Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. Let's try to recall what we were studying the last time around. We were looking carefully at the memory hold operation of the 1T 1C DRAM cell. In our concluding stages of the last lecture, we saw that through several mechanisms such as PN junction reverse bias leakage, gate induced drain leakage, subthreshold leakage, and also leakage through the non-ideal capacitor, there are many paths through which the charge in the so-called storage node can leak out. And because the charge in the storage node can leak out, it mandates that you have to keep restoring or refreshing the data or the charge or the voltage on the storage node. And this is where even DRAM derives its names from. Therefore, it is called dynamic random access memory. So today we are going to ask a very interesting question. That is, how frequently do you have to refresh the data or restore the data? So to answer this question, we have to recognize the fact that unlike what you may think, because of very many manufacturing variabilities and device operational variabilities, it is not true that every DRAM cell has one particular retention time. What is the meaning of retention time? Retention time is fairly simple. You write a particular value into the DRAM cell, into the storage node of the DRAM cell, and you keep periodically checking whether your external peripheral circuitry is able to faithfully read out that value or not. So for example, at time t equal to 0, you write 1 or VDD in your storage node, and you keep sampling at different time intervals whether your storage node value from the external readout circuitry can still be faithfully read out or not. And what happens is this retention time is finally what is going to decide what is the refresh rate of the DRAM cell. Now, as I have shown in this graph, that retention time for all the DRAM cells is not one particular value, but rather a statistical distribution. Okay, since it's a statistical distribution, we need to understand how to plot it. And this is done by this graph called cumulative probability percentage, which is a modified version of your CDF or cumulative density function. Okay, this is on the y-axis in log scale, and on the x-axis is your retention time. Now, without going into too much mathematics, let me try to tell you how to read this particular graph and extract some meaningful information out of it. Okay, so the meaning of cumulative probability is that it shows the accumulation of percentages as data values are added sequentially. Without making things complicated, it simply means, in essence, in this particular graph, it means that what are the number of cells in the DRAM array in form of percentage, or rather, let me paraphrase, what in this particular DRAM array, what are the percentage of cells that have, which are represented in the y-axis, which have retention time which is larger than that what is shown in the x-axis. So a very simple way to kind of understand this would be, just let's take some retention time. So let's take retention time of 1000 milliseconds, which translates to 1 second, and let's see, let's get a projection on this blue line. This blue line is actually the cumulative probability percentage function or measurement, and what we see is corresponding wherever it intersects what is the value in y-axis. So roughly, let me just draw it again. So from 1 second or 1000 milliseconds, roughly we see that the value for 1 second is roughly 0.01. Okay, so the cumulative percentage is 0.1 to 0.01. So that simply means that only 0.01 percentage of the entire cells have a retention time less than 1 second. So mostly all the cells in the DRAM array, which is what 100 minus 0.01, which is 99.99% of your DRAM cells, have a retention time greater than 1000 milliseconds or 1 second. So that is quite remarkable. You have just very few cells which have retention time, or 0.01 percentage of cells which have retention less than 1 second. However, as you can also see in the slide, the JEDC standard, JEDC is a industry consortium. So basically, whenever you want to build products, you discuss, there is a consortium of different companies which sit together and decide the standards. So the USB-C or USB-A or different kind of connector ports also come from these different committees which set up certain standards. So this JEDC standard or the JEDC specification, however, for the DRAM happens to be 64 milliseconds. Remember, only 0.01% of the cells have the only 0.01% of DRAM cells have a retention time less than 1 second. But for whatever reason, you have the JEDC specification saying that the retention time should be at least 64 milliseconds. The question is why? So if you think very carefully, you will get the answer that 0.01% may not look like a very large number, but if you multiply with the total number of cells, so generally total number of cells are in the orders of several GBs in forms of gigabytes. Okay, so huge, a billion or more than a billion cells are actually present in the DRAM array. Now 0.01% into 0.01 into 1 billion is also a very large number. It is still around 10 million or 1 million. Now, if 10 million and 1 million cells start failing because you have kept your refresh more than 1 second, your DRAM cell will not have very high reliability. So it is decided that the benchmark that you will keep is 1e minus 6 or 1 part every 10 to the power of 8. So only you set the DRAM standard of retention such that at a time only 1 out of 10 to the power of 8 cells is something that you cannot meet the specification for. And that is why you keep 64 milliseconds as the standard, as shown in this cumulative probability percentage versus retention graph. Okay, so how does the refresh happen? At a very broad level, we will go into device level very soon, but at the very broad level, as we have already discussed, that all the refresh happens essentially at the level of banks. However, one bank can have, in large scaled architectures or scaled memory arrays, one bank have many rows. Okay, so if you start refreshing all the rows in the same time, it will lead to very long refresh latencies. And therefore, to avoid these large refresh latencies, what happens is the total number of rows in a bank actually are divided into 8,000 in a group of 8,000. And this evenly distributed refresh latencies is what is facilitated during runtime. Basically, what I'm trying to say is that there are 8K auto refresh commands that are issued to refresh a subset of the rows in the 64 millisecond interval, because as you can see, every bank needs to be refreshed after the interval of every 64 milliseconds. And therefore, actually, the real rate of refresh in rows and columns is only 64 divided by 8K, which is roughly 7.8 microseconds. Okay, and a very interesting fact to note is, as you can understand, since refresh is happening continuously at such a fast interval, you will understand a lot of the area circuitry overhead the power consumption overhead comes from the refresh of the DRAM cell, and it is estimated that modern day DRAM arrays, almost 30% of the total power consumption is due to the refresh operation. Okay, so now that we have understood at a broader level how do you decide the DRAM refresh rates and how this is facilitated at the bank level, let us now start going and seeing how this is implemented at the cell level. Okay, so as we know, refresh involves first reading what is the value that is present in the storage node, and then you have to do a write back. Okay, and the natural question that we have to ask is refresh going to happen only because there is leakage to the storage node? The answer is actually no. The reason why you have to do a lot of refresh in reality, even when the DRAM is not idle, is the reason for that is that essentially the read operation in the 1T 1C DRAM cell is destructive in nature. Okay, what is the meaning of destructive in nature? And let us think why this cannot be non-destructive. The meaning of non-destructive or destructive is that once I do a read operation, the storage node the voltage in the storage node is completely disturbed. This is also called read disturb. Okay, so read disturb is an inevitable fact in 1T 1C DRAM cells. Why is this the case? Just compare it carefully with your SRAM cell. Why were you able to do non-destructive read in the SRAM cell? Because there was a positive feedback or positive regenerative feedback arising due to the cross-coupled inverter which was giving the memory effect in the SRAM cell. Now, in the absence of any such positive regenerative feedback, when you start reading some value, start disturbing the voltage values at the internal node or the storage node, it is but natural that it will be a destructive need. Please recall that a different scheme called the 3T1C cell was also discussed in the first lecture of the historical overview of DRAM cell, where you had connected the storage node capacitively with two more transistors, but very quickly we realized that scaling the 3T1C DRAM cell, the bit density will be very low because the area consumed by a single cell will be very high. So people decided, there was an overall consensus that let's continue with 1T 1C DRAM cell and try to implement and deal with the volatility which comes with the read operation, or the read disturb the problem of read disturb which comes with the read operation. Okay, so the essential point is that refresh is important not only when the memory is ideal, but also after each and every read. So let's see how that is facilitated. But before asking that, let's try to see what is the scheme or what is the voltage biasing scheme that is done during the read operation. So can I request you to just pause the video for just a moment and think very carefully. If you want effective read of both 0 and 1, remember when you have 0, the VSN voltage is 0, and when you have logic 1, the VSN value is equal to VDD. So the question I'm trying to ask is, please pause the video and try to think what should be the pre-charge value of the bit line such that you get effective read operation at both the values of 0 and 1, or 0 or VDD, where you get effective sensing at the end of sense amplifier for both values, stored values of 0 and 1. And if you think a little bit carefully, it is common sense that the pre-charge value for bit line, unlike SRAM where you were pre-charging with VDD because you had bit line and bit line bar, you don't have bit line and bit line bar, you have a single bit line. The value for that bit line, the pre-charge value for that bit line has to be VDD by 2. Why should it be VDD by 2? The logic is very, very simple. If the storage node has a value of VDD, what will happen? If this is VDD by 2, this is VDD. When the word line is connected, or when the word line is asserted, or the access transistor is on, there is a higher potential at storage node 1, storage node because of VDD, and VDD by 2 there is lower potential. So read current will essentially flow out of the storage node in the case that you have stored a value of VDD at V storage node. And the opposite is the case when you try to have a value of VSN is equal to 0. So if VSN is equal to 0, by the same logic, the potential is higher now at the bit line side compared to the storage node. And so the read current will flow into the storage node. And as we read, as the storage node, as the charge or the read current starts flowing into the storage node, there will be a negative change in the bit line, whereas there will be a positive change in the bit line. So in essence, what I'm trying to say is that when you have a storage node 1 or storage node VDD value and you pre-charge the bit line to VDD by 2, there will be a charging of the bit line because of a positive gradient between storage node to bit line. Whereas if V storage node was 0, there will be a negative gradient from VSN equal to 0 to VDD by 2 in V bit line. So there will be a discharge of the bit line, and therefore the change in bit line voltage will be negative. So this is very simple operation of the bit line value. And now we are going to ask a very important question, which I had kept in suspense for you. So we will now understand the read operation through this very simple diagram, very simple schematic, where we will consider that this complicated NMOS transistor is nothing but a simple switch. Now, let me motivate why we are trying to, do this before going ahead and doing the charge share analysis. The idea is very simple. Remember, we said when we were looking one class before at the construction of the DRAM cell in the fabricated chip, we saw that this storage node capacitor, although represented by this very simple parallel plate capacitor, in reality, when you actually fabricate it, is a very high aspect ratio elongated structure. And there I had asked you the question, why do you think that is happening? So now I'm going to answer this question. Why does CSN structure, in reality, the fabricated structure, have to be so complicated? So let's move ahead and try to discuss that. So as we had discussed, before the word line, before we switch on the word line is 0. So you can consider for an ideal case that this switch, which constitute of the NMOS access transistor, is on. So now what we will try to do is, remember, the voltage on the bit line is VDD by 2, and the voltage on the storage node, we are considering for the case VSN is equal to VDD, the voltage on the storage node is VDD. Okay. So what is the charge of this entire system once you have just pre-charged the bit line? You are about to do the read, but you have not yet asserted the word line. So what is the total charge in the system? So the total charge in the system is very simple. C is equal to Q, which is charge, is nothing but C, which is the capacitance, multiplied by V, which is the voltage, and that is what I have done. So the charge in the entire system, which is an isolated system, the bit line and the storage node are isolated, is nothing but CBL into VBL. So CBL is nothing but the lumped capacitance of the bit line. Okay, so lumped equivalent capacitance of the bit line is represented by CBL. So you have CBL into VBL is the charge on the bit line, and VSN and into CSN is the charge on the storage node capacitor. Okay, so this is the charge before. Now what I'm going to do is I'm going to just turn on the word line. I'm asserting the word line, and as a result, the switch will turn on. And what I'm going to do is, after the transients are done, I'm not checking the transient analysis. I'm just doing what happens at equilibrium. After a reasonable amount of time, when the current have flowed, why the read current has flowed and the charges have stabilized, what is the charge afterwards? And as we know, the charge afterwards will be V dash BL. What is V dash BL? The new voltage in at the bit line and at storage node. Now since they are connected, both are shorted, so bit line and storage node have the same voltage. We are indicating by VBL dash multiplied by CBL plus CSN. Why CBL plus CSN? Because here CSN and CBL are in parallel. So as you know, if they are in parallel, you have to simply add the capacitances. Okay. Now, common sense suggests that in a system, before and after, there has to be a conservation of charge. And that is what I am going to write down. I am going to equate the charge which was before I switched on the word line and after a long time after I have switched on the word line. And I see that if I just solve this entire equation and try to find out delta VBL. Now what is delta VBL? VBL dash minus VBL. So VBL dash is after the access transistor has been turned on and after the read operation minus before the read operation. So VBL dash minus VBL, which is delta VBL, will be nothing but CSN divided by CBL plus CSN multiplied by VDD by 2. And this particular small part, which is the ratio of CSN divided by total, CSN divided by CBL plus CSN, is called the charge transfer ratio. Why is it called the charge transfer ratio? The ratio between CSL divided by total capacitance of this system will tell you what is the amount of charge that will actually flow from the bit line to the from the bit line capacitance or from the bit line to the storage node. Okay, so this charge transfer ratio is very, very essential, and this ratio is very, very essential for this particular reason. For a very reasonable value, now let's start putting numbers. The typical value for CBL is roughly in the orders of picofarads. Now, if you want, I'm just giving an example. Suppose the storage node capacitance is just 10% of CBL and VDD typically is 1.5 volts. We will see that the delta V or the delta VBL will be just 70 millivolts. Now, this is very, very problematic because now your external sense amplifier circuit, remember, this delta VBL will go to the sense amplifier circuit, and this sense amplifier circuit is what will try to read the difference between the original CBL value and the final CBL value. Okay, and if there is not sufficient so-called sense margin, the technical term is called sense margin. If this delta V is not very large, it will start being affected by all kinds of noises in the system. Okay, so in essence, the point I'm trying to make is that as you start making CBL larger, why is CBL becoming larger? Because you are having larger and larger arrays. You are making bigger and bigger DRAM arrays. So as you make DRAM arrays bigger, you need to draw out larger bit lines, which will have larger CBL. The CSN also has to keep pace with it. The CSN or the capacitor of the storage node or the storage node capacitor has to keep pace. If CBL increases, even CSN has to increase. If you don't do that, this sense margin will become very tiny, and as a result, you will see that there will be big challenges or big problems in trying to get a reasonable sense margin. And this often will become a very big challenge, as we will see a few classes from now. Why will this be a challenge? Remember your textbook formula for capacitance. Textbook formula for capacitance simply says capacitance is equal to epsilon naught epsilon r A by D. Okay, A by D, where A is the area of the capacitor and D is the distance between the parallel plate capacitor. Now the issue is that as we are trying to make devices smaller and smaller, you're also trying to do area scaling. And the moment you start doing area scaling, maintaining a large enough capacitance on the storage node becomes very, very difficult. And that is why you go to these really weird aspect ratios or very weird kind of trench-like structures, which we will study about, in order to maintain a reasonable amount of storage node capacitance. Okay, so let us conclude today's class with this discussion, and in the next class I will go into more details about the timing diagram of read, write, and which will subsequently culminate into restore functionality. Thank you very much.